Hello, we'll be working chapter 3-4, problem 3-45. We've got a bucket hanging at D. We've got cables DB, DA, and DC that are holding it, and we are asked to calculate the force or the tension in each one of those cables. As you see my approach, I'll be doing a free body diagram, a position vector, a unit vector, and I'll be using my equilibrium equations. Now in the previous problem, we did not have to find a unit vector. That was because all of the angles were given to us. In this example, we are given units of length. So we have to find the point for each A, B, C, and D, come up with our position vector, then find our unit vector, then multiply it by the force, then find our equilibrium equations. Alright, so let's get to work. So I'm going to go ahead and cheat a little bit. And I'm going to go ahead and do this. And I'm going to say this is tension DC. This is tension DA. This is tension DB. And the bucket we were told was 20 pounds. That was also given. So this is my free body diagram. I could finish drawing these with dashed, and then I would give all my dimensions to the free body diagram. But to help with time, I'm going to leave it at that. So my solution. First thing I want to do is I want to find my points. The location, my Cartesian points. So I'm going to look at A, B, C, and D. So point A, if this is the origin here, that's 0, I'm going to be going 4.5 in the X, 0, and 3 in the Z. Point B, I've got 1.5, and then nowhere in the Y or in the Z axis. Point C, I got 0, 2.5, and 3. And then point D, I've got 1.5, 1.5, and 0. Okay, so solving for my position vectors then, dA is going to equal 3I. And how do I get 3I? Well, I'm going from D to A. So in the x-axis, I am moving 3. So if I'm looking at 1.5 to 4.5, so I'm going 4.5 minus 1.5 is 3I. Then I've got minus 1.5j, and then I've got plus 3k. dB, I've got 0I minus 1.5j and plus 0k. Again, dB from here to here. So the only thing I'm moving in is in the y-axis, not going anywhere in the x or in the z. So I'm only going to have my y component there. And then my last one, DC, I got negative 1.5 I. And how do I get that? Going from D to C. So I'm going up here. So my x, you can see I'm going negative. And that would be my distance of 1.5. And then I've got plus 1.0j plus 3k. Good. Alright, so I'll do the magnitude for dA. And we know that that's just going to be 3 squared plus 1.5 negative squared plus 3 squared, all square root, which is going to equal 4.5. So doing the same process for dB and DC, I came up with 1.5 and 3.5. So solving for my unit vectors then, so EDA, EDB, and EDC. So EDA, we know, is going to be 3i minus 1.5j plus 3k, all divided by the unit vector. So remember, our unit vector is the magnitude, I'm sorry, it's my position vector, is the position vector divided by its magnitude. So my magnitude on this one was 4.5. So I'm just dividing 3 by 4.5, negative 1.5 by 4.5, and 3 by 4.5, which comes out to be 0.667i minus 0.333j plus 0.667k. Here, we're just going to have 1.5 over 1.5. This was negative, so we're going to have a negative 1j. And then EDC, we had negative 1.5 plus 1.0 plus 3k. All over, which our magnitude was 3.5. Throwing this in our calculator, I come up with negative 0.4.29i plus 0.286j plus 0.857k. Alright, so now we're going to use our equilibrium equations. Sum my forces in the x, sum my forces in the y, and sum my forces in the z. Now remember, we will be multiplying this by tension dA, tension dB, and multiplying that by tension dC to get our f of x. So when we do this, when I sum my forces in the x, I get 0.667 here times TDA. Nothing here. We don't have a dB, so I'm going to go ahead and put plus 0 TDB. And then a TDC, I'm going to have 0.429. So I'm going to have a negative 0.429 multiplied by tension DC is all equal to 0. Summing my forces in the y then. I've got 0.333J negative TDA, because I'm multiplying, remember, I'm multiplying that all the way through. Now I have minus 1 TDB plus 0.286 in the y, but that's multiplied by TDC, and there's no forces in the y, so we can say it's all equal to 0. And the last one is my summing my forces in the z, 0.667 TDA plus 0 tension TDB, and then I've got plus this one here, 0.857 TDC, and I have my force in my y component, so that's going to equal 20 pounds, or I could say negative 20, and then that would be negative 20 and add 20 to both sides, and that would cancel. So if I look at this now, I can throw this into my matrix, and I can say 0.667, 0, negative 0.429, negative 0.333, negative 1, negative 0.286, 0.667, 0, and 0.857. And then over here I'd have 0, 0, and 20. So again, this would be my A, this would be my B. So all I did was say 0.667 here, 0 here, negative 0.429, negative 0.333, negative 1, negative 0.286. Okay, so that's a negative, so let's come back here and let's make sure I have that right. That should actually be a positive. So going back and checking is always a great thing, if you notice, because I would have messed that up pretty good. So this is 0.667. That would be 0. This would be 0.857, and then this was 20, and this was 0 and 0 here. Okay, good. So now, again, throw this in your calculator, save you a bunch of time, and I can calculate that this was TDA, TDB, and TDC. Using my calculator, I came up with 10 pounds, 1.1 pound, and this was 15.6 pounds. And those would be my answers. So if you have questions on this, please, again, throw them on the discussion page. If I need to go back and work something out or explain something more, I can be happily to do that. All right, thank you.